And I'd like to hand it over to Javie Franquet and his talk on Tectonic Boundary-Condition Insights from Borehole Breakouts.
All right, sorry for that. Thank you for the opportunity. So I'm going to show you a few examples of breakout. That's all I'm going to share today, many breakouts, no induced fractures. So it's very focused, the topic today, but it's very critical. It is very critical to understand the stresses, to understand how these breakouts are created, and to de-risk any geomechanical analysis that are coming after calibrating the stresses. So there are many insights that I'm going to share today. So these are, for example, breakouts on a borehole image. So this is essentially an image, an acoustic image log with actual breakouts. So these are irrefutable evidence of shear failure around the wellbore. And what we're trying to essentially do is to reproduce. This is a simulated breakout, and we're trying to be honoring as much as possible the width, the width of the breakout and where they are occurring to get the stress calibration as accurate as possible. So today I will be talking about dual, triple, and quadruple breakouts, where and why these things happens. More importantly, I will talk about how to model these breakouts, how to use different failure modeling to get this breakout, essentially changing the boundary condition, the tectonics, and see how we can reproduce those borehole failures evidence that you can see very clearly here in this image. You have resistivity static, resistivity dynamic, a borehole acoustic with the amplitude and travel time. So you can definitely see breakout happening. And more importantly, you can see places where they don't happen. And that's what I'm going to address today. Why a breakout is not happening here, here, or there, and when they're happening here. So it's either stress, it's either different strength, and all of these questions that we are definitely intrigued by the nature of these breakouts. So dual breakouts, triple breakouts, and quadruple breakouts. So these are irrefutable evidence. I mean, today we have magnificent borehole images that we can acquire this borehole-induced failure. The most common ones are the dual breakouts. They happen almost everywhere in different rock types, in soft rock, in hard rock. They happen in vertical, horizontal wells, and they are very well studied. And the main takeaway of these breakouts on vertical wells is that automatically give us a direction of the horizontal stresses. So that's one of the main understanding of the main insight when we see breakouts on a vertical well, for example. So that gives us the directionality of the principal stresses in the horizontal plane. Now, triple breakouts, these are more interesting and they're very rare. I have only seen in weak sandstones. I published a paper back in 2008 where there was a lot of conversations and discussions about it. We see them in 3 different log services. It was not only one service provider. We run the 3 major service providers in this field, and all of them were acquiring these triple breakouts. So there was not something unique to a particular well. We see them across the field. And one of the things that are unique about this is are essentially happening isotropic stress condition, which is very rare. It's very it's not very common to get that condition, and they were actually reproduced in the lab. So I'm gonna talk about more about this. And of course, so because it's isotropic stress, you don't get a stress direction out of 3 triple breakouts, right? So now moving into the quad breakouts, there's a lot of work on this from Solvac and Julie Cohen, especially in the Marcellus shales. These are happening when a particular rock type, you need to have a weak bedding planes, so you need an isotropic rock that have a weakness on a particular plane, and typically these are laminations that are horizontals in shales type of rock. And these happen in highly deviated or horizontal wells, very common in horizontal wells, unconventional. So mainly are attributed in shales. So triplet and quadruplet are more rare, but they are possible to happen. So now let's see the dual breakout in more details. So we know that there were a lot of discussion about the nature of how these breakouts were created. Mauri had a very nice publication discussing about the splitting of the tension using a modified stress intensity concept and a variable elastic moduli around the wellbore. With the basic elasticity and molecular failure criteria, it's more understood about a shear happening in the direction of the minimum horizontal stress. So you have a depth of the breakout, and then the shear essentially is created in this area, and the width of the breakout is between the distance between the two green points. So we know now that these breakouts are primarily due to shear, and since we have three principal directions in around the wellbore, it is created by the stress anisotropy, and the most common anisotropy, of the biggest anisotropy, is created by the hoop stress in the direction of the sigma h mean and the radial stress. So this is the configuration we typically call it the dog ear breakout, because the shear is happening in this fashion here. And they're typically elongated in a particular structure or a particular lithology interval. But possibly we can end up with toric breakout, and these are more aligned with the one of the principal stresses is vertical or aligned to the wellbore direction, and the minimum direction is essentially radially to the wellbore, and that creates the shear in this plane. So now the triangles, I don't know if you notice, is in a vertical plane, whereas the triangle here or the shear are created in the horizontal plane. And the other possibility is now the minimum principal stress is now the hoop stress, and the maximum is elongated to the direction of the wellbore. So these are the three possible shear mechanisms. The most common one is this one, due to the fact of the stress anisotropy, but it's always important to check for these breakouts doing the stress analysis. This is a more detailed images of the three type breakouts. So in the mode one of the dog ear breakout, along the wellbore, around the wellbore, the tangential stress is the maximum principal stress, and the radial stress is the minimum. So the shear happens in this plane, and that's why you get the breakout in these areas, in the direction of the sigma h mean. Now the toric, the hoop stress is in the intermediate principal stress, and the maximum is along the vertical or the wellbore axis, and the radial direction is the minimum. And then the shear is in this plane, and that's why the triangle is now looking at getting into the well like this. These are the shear that create that breakout. And finally, the helical breakouts are the shears are happening because the axial stress or the longitudinal stress is the maximum, and the minimum is the hoop stress. So now the shears happen like this, and these are helicoidal stresses. Now, talking about the triple breakout, as I said, they are more rare, and actually there is a lot of work on this from University of Wisconsin, and this is a stress polygon, and this is one of the publications that really encouraged me to write this paper in 2008, because there was a lot of controversy saying that these breakouts were created by the drilling, stabilizers. And we proved in one well that actually the orientation of the stabilizer were not matching the triple breakout. So we come up with the conclusion that these are real and happen in nature. So it was very encouraging to see the reproduction of these triple breakouts in the lab by Professor Hampson, based on Hampson in 2007. So he reproduced breakouts in normal stress regime. So in order to produce triple breakout, you need to be in this green lane, so isotropic stress condition. So the two horizontal stresses needs to be equal. In this case, 60 megapascal, and the vertical stress was about 70 megapascal. So that's a normal stress regime, and they were created in the lab. As well in the reverse stress regime, this is Cordoba cream sandstone. They were also created on the reverse stress regime. So now the vertical stress is only 10 MPa, whereas the two horizontal stresses were equal to 40 MPa. This figure here is actually very clear to see the shear happening, but the actual chip of the breakout has now fallen into the wellbore. So very interesting to see this in detail. More pictures about triple breakout in Berea sandstone. And so we know this happened. It's interesting that it cannot try to create a triangle shape. So from a circular, it becomes a triangular shape and it becomes stable for that isotropic stress condition. So very interesting. If you ask the question if you can have dual and triplet breakouts at the same time, the answer is yes. This is a borehole image where you have a poorly consolidated sand here and you have the triple breakout very clearly happening. And then this is the shale. Now the shale has more integrity, has more stiffness, high Jones modulus compared to the poorly consolidated sand. So there is a stress anisotropy in the shales. So that's why you see the traditional dual breakout. So this is very interesting because you can get the stress direction here in the dual breakout. And then looking at the triple breakout, they were happening almost randomly with a primarily dominant that one of the breakout was actually aligned to the minimum horizontal stress, whereas the others were 120 degrees apart. This was a very insightful. This is something that we didn't know, so I'm happy to share this observation in this forum. Now, talking about the quadruple breakouts, and there was some conversations in the chat about this square wellbore. Yes, square wellbore actually happens. And this happened in this type of condition drilling. As you can see, this is a deviated well modeling a breakout with plane of weakness. So these planes here represent those plane of weakness or lamination. And as the well gets deviated, you can clearly see how the traditional dual breakout is starting to become a double knot or a double loop type of breakout, essentially because those bearings here create that shape and create that stress concentration that produces failure that reproduce as kind of in this figure here. This is for actually a borehole a borehole image of the like a caliper, an acoustic caliper around the well, and you can clearly see that this is essentially the shape of that well becoming square by the product of the plane of weakness in this shale. This is happening in Narum Shale in offshore Abu Dhabi. There are many publications, Susaka in one of the fields and Hemat Singh in one of the neighbor fields as well, observing this type of breakout. And it's very well documented in Sobak Borehole Geomechanics, Reservoir Geomechanic book, where you can end up with 4 breakouts due to the plane of weakness failure. So now, how are we going to model these breakouts around the wellbore? So 2 stress transformations are required. The first one is from the earth coordinate system to the wellbore coordinate system. So this is a very simple tensor rotation using the deviation and azimuth of the wellbore. So these are the two angles that are required, wellbore azimuth and inclination. So you put this rotation matrix in both sides of the tensor for the air coordinate system, and then we change it to the wellbore coordinate system. Once we get that, then we need to convert it to a cylindrical coordinate system, and essentially we get the principal stresses in axial to the wellbore, radial to the borehole, and tangential. So, and these are the three principal directions that we're going to be looking at around the wellbore for any arbitrary well deviation or azimuth. So to model this breakout, there are essentially two things that we need to compare. One is the rock shear strength, and in this particular case, we are using the very simple Moore-Coulomb failure criteria. So it is the same around the wellbore. Other failure criteria actually varies because depends on an intermediate stress or depends on and stress around the wellbore. So the rock strength actually changes around the wellbore. But assuming a Moore-Coulomb failure criteria and assuming a mean stress to get the confined shear at that condition, or the maximum allowable by the rock, or the maximum shear that the rock can sustain, then we can compare it to the shear around the wellbore. And when that curve, the blue curve, is become higher than the strength of the rock, is that with the breakout. And this is how essentially we model this distance represent the distance of the breakout, and we do that depth by depth along the wellbore. So the idea is to reproduce what we model with what we see from the borehole images. And with that is difficult is because we need to change the model, and we need to change our boundary condition. So this is more in detail about the workflow. The on the left hand side is how to get the stresses, the horizontal stresses by depth, and the other side is the borehole induced stresses, the two rotational transformation, and including the shear failure criteria, and essentially getting the breakout simulation, like in this case. So it is a loop because we don't know the stresses, we know the breakout, so we need to come up with some assumptions. And the main assumption here, well, there are two. One is the poroelasticity. How important is poroelasticity? So the bio coefficients. I actually presenting a paper next year in the IPTC that's going to discuss 7 different calibration methods by adjusting poroelasticity with constant bio, lithology dependent bio, and also the tectonic strain calibration. So this is a very insightful paper. I will put the reference in the chat for the ones that are interested for that. So this is a interactive workflow because we need to put some assumption here and see the breakout and compare to the image. And if we need to tweak the boundary condition, we do that. If we need to play with the bio coefficient, we do that in order to get as much as representative of the model. Like in this case, these are the actual image, and these are the simulation of the breakout. So let's see some examples. So in this particular case, I'm showing the gamma ray resistivities, density neutron, mineralogy. So you can see a beautiful carbonate here in top of a sandstones. We see we run an isotropic model in this case. So we have Jones modulus and Poisson ratio in the vertical and horizontal directions. We have here the UCS and the friction angle. So I want you to focusing on this because the tendency to understand breakouts is that they typically happen in the weak rock, right? And this is exactly what is happening here. If you look at the UCS, the UCS is lower in these areas here, where I shade, and that's correlate fairly well to where the breakouts are happening. So that's one of the observation here, that the breakouts are essentially forming in the lower sand, not in the carbonate, which is actually faster and stronger. Then the image, when we model the image, we notice that the UCS actually is a very good proxy to see the breakouts. So the only problem is essentially the vertical resolution. As you can see, is very difficult to match. If you're zooming, it's very difficult to match a small breakouts like here and here, where the UCS don't have that vertical resolution, or mainly focusing on the acoustic. So in that case, we probably need to enhance our formation evaluation to a high resolution, either the density or the acoustic. The acoustic can be enhanced from 3.5 feet to maybe half a foot. It can be enhanced by different stacking of the full waveforms. This is something that any geoscience center of the major service providers can do. And another possibility is actually using the resistivity image that has the highest vertical resolution and get some density, or from resistivity to density interpolation or correlation to get a high vertical resolution properties. But something interesting here happened, and we see very clear breakout here where apparently it's actually a dense zone, and we couldn't really explain, or we couldn't really reproduce those. So we know we need to come up with a more robust boundary condition and stress profile to actually reproduce those breakouts that we can with this simple and basic modeling here. So this is an example of this is in the Middle East. It's a Thai sand type of reservoir. Very clear breakouts. I mean, these are many breakouts, as you can see. This is about 10 meters, so to give you an idea of the scale. And the question here is, okay, where the breakouts are happening? Well, they are happening predominantly in the sandstones, but it's very well constrained by thin beds. As you can see, there are very clear breakouts that are very well constrained on the beds. And you can see from the resistivity image, it's very highly laminated. So we need to come up with something better than the very robust DTC and DTS and density, which are at a higher sampling and not so much vertical resolution. So so the breakouts are happening in the low strength, and that's consistent with our intuition that the breakouts happen in the weak rock, like here, for example. This is the friction angle. So essentially, it's a low friction angle, it's a low density, it's a low UCS. So that's and when the UCS is high and the friction angle is high, then there is no breakout. So this is coming to our basic intuition. Okay, and when we essentially come up with a very high, this is the stiffness, or it's a proxy of the Jones modulus. This is actually coming from the resistivity image. We use the higher vertical resolution from the resistivity to come up with a density, and from the density we get the stiffness. And with this high vertical resolution, then we did the breakout modeling, and we come up with a stunning match. I haven't seen a modeling so much in accordance to the evidence. So so that gives you a very confident that the stress profile and the rock properties that you're using are very well in accordance to the evidence of from the borehole images. So so this is in the case of a highly laminated formation where the breakouts are happening in the weak and low stiffness layer. Now, if you have seen breakout long enough, you know the breakout sometimes happen in the strong rock. And these are a little bit more interesting because if you use the same boundary condition, you will never match those breakouts, okay? Because if, for example, if you look at here, this is the compression and shear way slowness. So when the shear goes this direction is slow. So this is very clear that this is a very slow as a shale, so no breakout. And then in the fast, when the DTC and DTS goes fast, then you see the breakout. And it's very consistent. The fast, you see breakout. The slow, you don't see breakout. So if you put a stress here with no tectonic boundary condition, you will never get the breakout. You'll get the breakout here. You get the breakout in the weak zones, not in the strong rock. So this is where we need to come up with a different boundary condition. And that's essentially what we did here. We add the tectonic strain into the stress profile. And by adding this term, essentially we're multiplied by the Jones modulus. So because the Jones modulus is higher here, the horizontal stresses and the horizontal anisotropy is higher, fundamentally higher. So this is happening trying to crush a Oreo cookie stacking. So the stresses is essentially carried by the cracker, not by the cream. The crackers are the ones that are going to hold the majority of the horizontal stresses because they have high stiffness. So the rock that have high stiffness is the rock that's going to contain more the tectonic stresses, and therefore, even though it's stronger, it's gonna has a shear failure compared to the soft layers that are weak, but less stress anisotropy and less stresses due to the tectonic component here. So this model is essentially required for this type of borehole breakout. When you see breakout happening in the strong and high Jones modulus layers, then this is the correct modeling to reproduce those breakout. This is essentially what we discussed. This is another example. You see a very nice combination of sands and shales. And you can clearly see the breakouts happening primarily on the sandstones, not in the shales. And again, these are the rock that are fast compared to the shales that are weak and slow. So definitely these two models, the no tectonics and the additional tectonic stress boundary condition, will not be able to reproduce these breakouts because you're going to end up with breakouts where not happening and no breakout where they actually happening. So this is the model with the tectonic strain as a boundary condition that is required to reproduce these breakouts successfully. So these are one of the main takeaways is to look at where these breakouts are occurring. If they are occurring in the high stiffness or the low stiffness, so you can use porosity or density or acoustic velocity to get that as a proxy, which ones are high stiffness and which are low stiffness, and use the correct boundary condition for the stress profile. Now, as our conclusions, so breakouts are most commonly produced by shear, as a shear failure localized around the wellbore, primarily by the high hoop stress, the tangential stress. And this breakout happen in the direction of the minimum horizontal stress. In generic term, it will be the minimum stress in the transverse plane, but if the well is vertical, that will be the two horizontal stresses. Triple breakouts are more rare and so far only observed in nature, in vertical wells, in poorly consolidated sandstones under isotropic horizontal stress condition. They can be reproduced in more competent rock like sandstones, but not commonly seen in borehole images. So far, we have only seen in poorly consolidated sands. They're very soft and plastic. That's why the horizontal stresses tend to be isotropic. Now, quadruple breakouts are formed in highly deviated or horizontal wells that are drilling through shale formation that have weak bedding planes, like I show in the two examples from the Middle East. When we see breakouts in very laminated formation, it is critical to get high vertical resolutions of logs, either acoustic or the imagings can be used to get very high vertical resolution in order to get the full representation of those breakout. And last but not least, so breakouts that are created in low strength or low stiffness rock, they can be modeled by tectonic stress condition. We can add an additional tectonic stress just to match the minimum horizontal stress. But when the breakouts happen in the high stiffness layer, which I showed two examples of those, we need to change the boundary condition. It has to be with the lateral tectonic strain. So now we need to put strain as the boundary condition. Then we have the Jones modulus multiplied by that, and therefore get the right stress profile across the formation. So, and all of this insight can only be made by looking breakouts. Without that evidence of the wellbore, it will be almost impossible to understand what type of boundary condition we need in the far field stress to understand the stress profile. Again, that's all I have for today, and I would like to thank Baker Hughes for the permission to record this presentation, and also I would like to thank Stephen Dimmock. He helped me a lot on sending very nice examples of breakout, so I was able to do the modeling and bring these insights to you all. And here are my references today that are discussed. So you can go and click on the link and get more information from this publication. Now I'm open to answer any question if you may have.
Thank you, Javier. Do we have any questions? David, you're first.
Very nice presentation, Javier. Thank you. I just didn't see BIOT's profile. I just want to know, are you using a constant BIOT or are you calculating a profile?
Yes, constant BIOT is a simplistic method. The paper that I'm gonna present in IPTC covers 7 calibration methods. So for the no tectonic, it has constant BIOT and lithology dependent BIOT. The third and the fourth method is actually with tectonic stress boundary condition, again with constant BIOT and a lithology dependent BIOT. And the tectonic strain, we are proposing 4 different methods, and we cover all of them. This example here, they use BIOT as a proxy of porosity. So we use porosity to get a lithology dependent BIOT because it's a component that changes your effective stress and therefore changes your occurrence or not occurrence or breakout. So if you are dealing with a very consistent type of rock, let's say you have a massive carbonate and a massive sandstone, you can probably get away with a constant BIOT as long as you put more or less the right number, 0.7, 0.8, depending on how tight it is. But when you're dealing with a stacking of different rock types, like shale sand, or tight, dense rock, and then you have a porous rock, then it's fundamentally important to put a BIOT that is actually changing. Because if you put a constant BIOT, you will never reproduce the breakup. I can tell you, done that, been there, is not happening. Yeah, that's my recommendation. Yeah.
Completely agree. Thank you very much.
Mm-hmm.
I see we have some questions in the chat about making the presentations available. We will check with the authors, and if they all agree and can make PDF versions, then we will make the presentations available somewhere on the Borehole Image SIG page.
Yeah, absolutely. No problem from my side. I can make those. I can create a PDF and send it to Peter. So Peter, you can distribute to the rest of the SPWLA organization committee.
Well, yes, I will do. Thank you.
Okay, thank you, Peter.
Do we have
not to mention that? Oh, sorry, Peter. Not to mention that some of these presentations will be available on the SPWLA YouTube site as well.
Javier, Roberto Berto's asked a question.
Okay,
If we think
I cannot see the chat.
All right, let me read you the question.
Okay.
If we think to possible future machine learning approaches to detect in an automatic way the stress-related features by borehole image, do you think that these synthetic outputs of models could be in such way included in order to be taken into account for a process of classification?
Yeah, I read a very interesting paper recently about using artificial network. Not completely an AI type of approach, but it is it's definitely a possibility. As long as the input data is good and consistent, I think the neural network will find a way to reproduce them. I will certainly supervise the output on maybe restricting the some possible scenarios of somebody is talking on can you please mute?
Yeah.
Somebody's talking at the same time.
Person.
Okay, Javier, unmute yourself, please. Javier, you're muted because...
Sorry.
My fault. I had to mute everyone because we had someone talking. I can't do individuals always.
Okay, thank you. No problem.
Thanks.
You muted again.
Okay. Just to say about this neural network, something that is important is to have some supervision of what the code is doing. Because remember that the breakout is an equation that have two unknowns, right? So if you only have breakouts and you don't have any other information, you have infinite solution. You can reproduce the breakout by an infinite combinations of, if the well is vertical, any combination with maximum and minimum horizontal stress can actually reproduce that breakout because it's an equation with two unknowns. So now you need to constrain either with a microfracture or either with another observation that can constrain the minimum horizontal stress, and then you have the flexibility to use the maximum horizontal stress. I've been using microfracture data because the microfracture data get the breakdown that can easily be calibrated with the two horizontal stresses, and also you get the fracture closure. So you get two measurements, and it's very unique solution when you get that. And if on top of that you have a breakout, then you have a perfect data set to be 100% reliable. There is no room for error. If you have a series of microfracture and on top of that you have few breakouts, you know that you're going to reach a unique solution to honoring both the microfracture test and the borehole failure evidence. So when you put all that data to an AI, you need to be reliable that it's going to be using accordingly to not come up with something that it will create an earthquake, some stresses or stress anisotropy that are not realistic, because that's something that could happen, right? So, but yeah, definitely, I will say an artificial network or AI is a fantastic tool get this process more quickly, more enhanced, and do this almost on the fly. Ideally, you would like to get this as soon as you see a breakout when you're drilling, right? So absolutely, that's a very good possibility.
Thanks a lot.
Mm-hmm.
Thank you. Do we have any other questions? Well, thank you first to our 4 presenters. That was 4 great presentations today and very much appreciated. We did have a lot of interest in this topic, which is why the next session, which we haven't decided when it's going to be yet, it will be in the new year, will be a continuation on geomechanics and borehole images. And we look forward to that one as well. Please do send us any suggestions for workshops which you'd like to see and like us to put on for you. Again, this whole special interest group is for you, so we really want to help you with any questions that you may have regarding borehole images.